Okay, so what I did just now is I gave you this necessary and sufficient condition for being solvable. And I'm going to give you a generalization of this and an application to a question of decidability. So this was the, so let's say we want to tolerate, say, only T, we want to be T resilient instead of weight free. So weight free says we tolerate n failures out of n plus 1. You might say, well, that's kind of expensive. Google has 5 million servers, and they don't want to tolerate 4,999,000, et cetera, failures. They probably don't expect more than 10%, on a bad day of failures. So it's interesting to look at systems that tolerate fewer failures. Or you can say, well, read-write memory is so passé. Modern architectures give you things like test and set and fetch and add and so on. And what happens if I can do that in addition to reads and writes? So we're not going to we're going to come back to this question in more detail in a later talk, but now we're going to sort of dip our toes in this kind of question. And I'm going to say, well, suppose we have weight-free read-write memory augmented with a black box that does k-set agreement. So we know you can't do k-set agreement and read-write memory, so I'm going to give you this kind of k-set oracle on the side and ask what happens there. Now notice if you're T resilient, then you can do set agreement because you can sit around and wait for n minus T processes to show up. Choose one of those values, and that will give you n minus T set agreement. So this is a kind of an oblique sideways approach to T resilience. So I'll give you read-write memory and this little black box oracle on the side, or actually maybe many of them. Okay, so again, if I could do max T failures, I can do T plus 1 set agreement. If I have test and set, I can do set agreement up to half the number of processes. You put them together in pairs, they do test and set to decide whose value wins. And so lots of alternative models are equivalent to read-write plus k-set agreement. We're not going to go into detail now about what they are, because we'll do that later on.
Doesn't show equivalence. Shows that if we have a handle on that, we have some
idea.
So it's not.
Yeah. It's not equivalent, but if I can tell you what you can solve with read-write memory in a black box, then you can solve that with in a T-resilient world, because you can run a weight-free algorithm in a T-resilient world. Okay, so here is the theorem for this augmented kind of memory. So we solve this colorless task, and we say this has a weight-free read-write protocol. This should be read-write plus a black box. So we have another read-write plus black box, if and only if there is a continuous map, and this is what we said last time, but now we're going to the skeleton instead of the whole thing. So the effect of having a k-set agreement black box is we can have holes in things now. Whereas before we didn't have holes, now we can get them. And we only need to map the skeleton into the output complex and not the entire protocol. And in particular, notice that if k is 1, the zero skeleton is just disconnected vertexes. And we can always, this always exists. So it says that if you had consensus, you can solve any of these problems, which is a kind of a backdoor path, topological path to the universality of consensus. That's a consequence of this.
So by consensus, you can solve any colorless?
Any colorless task, yeah. You can actually solve any general task as well, provided you can express it in terms of this relation. There's some technicalities. I can define a task that can't possibly be solved in suppose I say I want the sum of everybody's input. There is no way you can write a T-resilient algorithm for that, because if somebody crashes, you can't ever figure out the sum. So there is a kind of a technical condition that says that really there's got to be some hope of doing it, namely that you can always, given any subset, you can decide an answer. So again, the idea is that adding the k-set agreement lowers the condition from the entire complex to the k-1 skeleton. So we started out looking at mapping the entire skeleton over, and now we have a weaker condition because we can erase parts of the skeleton. So it's easier to find a map from a skeleton than the whole thing. So you can see that this tells you how adding k-set agreement black boxes increases your power. So two directions. This one will turn out to be easy. We go from protocol to map. So without loss of generality, I have a k-set agreement box. Let's say that if fewer than k processes participate, then in your k-set agreement protocol, then everybody gets their own input. So that just says that if it's, this is an easy way out. We can always simulate that by, putting a wrapper around it. So that's okay. And that's indistinguishable from reads and writes. Okay, so the proof outline is, remember we did this inductive construction from the skeleton to the protocol complex as part of the proof of the original theorem. So now we're just going to stop at k-1. And with if you have fewer than k participants, then adding a k-set agreement protocol doesn't help you any, because you could have done the same with read-write memory anyway. And so we just we stop the construction to one direction at the right dimension, and then we take the same decision map and compose it just as before. So this is pretty easy. So now we want to go the other direction. Given a map, I want to do a protocol. And here the idea is also fairly simple, and I'm going to just illustrate it by showing you pictures. So here we have the colorless input complex, the output complex, and we have a continuous map from the one skeleton. So not from the entire solid triangle, but only the one skeleton. So there could be a hole here, for example. It's continuous. So we can take the simplicial approximation on the skeleton, and it looks like this. Okay, so here is how our algorithm works. So everybody starts out on the corners of the vertex. They do k-set agreement. So they drop down from a bunch of dimensions. And then once we've agreed on the vertex on the skeleton, then we run the k-set agreement to drop down. Then we look at the simplicial map, and we run barycentric agreement. But now we're doing barycentric agreement on the skeleton rather than on the original thing. And then we apply the map, and we're done. So you can see this is a fairly straightforward construction. The algorithm is the same, except that we have a earlier phase where we call the k-set agreement black box. And the interesting thing here is that the complexity is the same, because we run k-set agreement once, and then we do the n-fold barycentric agreement apart the way that we did before. So this says that if you have a k-set agreement protocol, you only need to use it once to get the full power. Use it once at the beginning. And so there we go. So what we've just shown. Oh, just to be specific. Oh, okay. Yeah. So it could be, in general, this would be like a k skeleton. So this would be k-1 skeleton, because we have two-set agreement. So, so obviously that wasn't a proof, that was a picture. But I'm confident you could reproduce the proof based on the picture. Okay, so the very last thing I'm going to do is some decidability results for wait-free read-write memory. So a lot of what we've been doing here is I give you a task and say, like set agreement, and say, no, this can't be solved. This has no solution. Or another task like barycentric agreement and say, yes, it can be solved, here's a protocol. And question is, well, what if can I program a Turing machine to do this? So let's fix the wait-free read-write model. And a task specification is a finite input complex, a finite output complex, and a finite relation, so everything is finite. Can I write these down on my Turing machine tape, crank it in, and produce PODC papers? And if I did that, then I could automatically generate the conference papers, and then I wouldn't need grad students to help me write these things. And I could save a lot of money. I could spend all that money going to Rio for Carnival instead of paying their stipends. So this seems like an interesting research problem. But the answer is no. It turns out that in general these things are, whether a protocol exists for a task in read-write memory for 3+ processors, it turns out with read-write memory and k-set agreement is undecidable. Actually, k has to be greater than 2, and the number of processes has to be greater than 3. But that doesn't leave much for automatic generation. Okay, so I'm going to prove this by giving you a particular set of tasks, a family of tasks, which together with the theorem about colorless solvability will be fairly straightforward to see it's undecidable. We'll need to quote some classical results here. So we start out with a simplicial complex. So now I'm going to define the terminology used to define the problem. And a loop here is just what you think it is. It's a sequence of edges that goes around, and the endpoint is the same as the beginning. We don't care. This is a simple loop. It doesn't intersect itself, but it could. We don't care.
This is in the one skeleton.
Beg pardon? Yeah, in the one skeleton, yeah.
What is a higher dimension loop?
Oh, we don't need higher dimensions loop. Yep. So here, this is just a one-dimensional. Basically, it's a circle, continuous image of a circle in the loop. And then after picking a loop, I'm going to pick 3 distinguished points I'll call rendezvous points on the loop. And the input, I'm going to define, will be a 3-process, or actually it's a colorless task. It can be any number of processes, but you have to have at least 3 for this to be interesting. And so the input and the output complexes are the same. And their rule is that if everybody starts out, everybody's going to start out on one of the rendezvous points. So the input is just the 3 rendezvous points. And the rule is that if everybody happens to start out on the same rendezvous point, they stay there. That's rule number 1. Okay, rule number 2 says that suppose they start out on 2 of the 3 rendezvous points. Then they have to basically converge to some edge on the loop between those 2 points, where between is the loop segment that doesn't contain the other rendezvous point. This is no higher dimensional anything. This is all 3 rendezvous points. And it's okay if they converge on a single vertex. It's okay if they converge on the vertices of a single edge. But those are the only choices. So this is a little like the barycentric agreement. Okay, rule number, bug on 94. Rule number 3 is that if they start out on all 3 rendezvous points, then they can converge anywhere they want. But they have to converge. So they have to, it's okay if they end up on a simplex, it's okay if they end up on an edge, and it's okay if they end up on a triangle. And if there were more than 3 processes and this were a higher dimensional simplex, then they could converge on a tetrahedron. So as long as they converge somewhere, we don't care. So that's 3 rules. It's colorless, so we can have as many processes as we want. And it's a family of tasks because this could be any simplex and could be any loop in the simplex. So that's what we're quantifying over. Okay, so the key idea here is the notion of contractibility. So a loop is contractible if I can continuously deform it to a point without leaving the complex. So I can take it and squeeze it. So this loop is contractible, and this loop is not contractible because there's a hole here. That's an obstruction to contracting it. There's no way you can bend or stretch it to get it to go to a single point. So some loops are contractible, some aren't. No, because if you try to kind of wrap this around, no, even if there were only one hole here, you couldn't do it.
If there was a,
Big one? Yeah. You know, so you can't. I mean, not that it matters, but in this case, but. Okay, so what I claim here is that the loop agreement task is solvable if and only if the loop you chose is contractible. And why is this? Well, our input complex consists of a triangle, right? Because you have 3 vertices you could end up on. And our theorem says that any colorless task is solvable if and only if there's a continuous map from this triangle to the output complex that matches the delta. And what does delta say? It says, well, each vertex has to end up here. Each edge has to end up on the thing. And the interior, we just have to fill that in somehow. But contractibility turns out is undecidable. That a simplicial complex is a finite structure. A loop is a finite structure, so you could put them on a Turing machine tape. But it turns out that there's a classical result that says that even for finite complexes, the question of whether an arbitrary loop in an arbitrary complex is solvable is undecidable. Why is this? Well, proving why would be way beyond the scope of this course. But this reduces to something called the word problem for finitely presented groups, which says that if you give me a finite representation of a group with words and relations, and give me an arbitrary word in that group, any arbitrary sequence of symbols, and ask me, given these reduction rules, is this reducible to the 0 element of the group, the unit? That's undecidable. And again, why is this? Well, that in turn goes up to some two-dimensional Turing machine thing that I've never actually seen the original paper. Actually, Michael Rabin wrote one of the early papers in proving this. This was proved in the 50s sometime, and he wrote the second to the last paper in this sequence. Okay, so that implies it's undecidable whether a loop agreement task has a protocol in wait-free read-write memory, and in general that means that there exists an undecidable family of tasks in read-write memory. Okay, well, how about other models? So how about case-set agreement? I'm going to give you case-set agreement now. Now, case-set agreement, remember, gave you more computational power because it lowered the condition. It weakened the condition you had to satisfy. Now we need continuous maps from skeletons and not from the entire thing. And so we know it's solvable if and only if this function, this continuous map exists. But if you're talking about the skeleton, for k greater than 2, then that still means that the loop has to be contractible. Because you're still you're mapping from the skeleton, but it's still solid triangles and stuff. So it's undecidable whether a task has a protocol in wait-free read-write memory plus case-set agreement if k is greater than 2. But what about two-set agreement? Or what about one-set agreement, consensus? So are tasks decidable if you have two-set agreement or consensus? So again, if and only if the map from a skeleton exists. So for consensus is always solvable. So there's always a protocol. So the Turing machine that always halts and says yes decides any task if you have consensus. And this is the universality of consensus showing up again. If k equals 2, it's decidable. It's not always solvable, but it's decidable. And that's because path connectivity is decidable. So what this is saying is there a, given these vertices, is there a path between them? And path connectivity is not just decidable, it has polynomial time algorithm. And so these special cases are decidable in read-write memory, and everything else is undecidable. And if we have time later on, there's more general characterizations of when tasks are decidable, what kind of models. But summarizing somewhat, if you can do two-set agreement in any model, then things are decidable, and if you can't, they're not. Okay, so this was a shorter lecture, but I gave you a lot of vegetables to chew on. So what we'll talk about next time is, so all these results are for wait-free read-write memory, and we're interested in other kinds of failure models. So next time I'll introduce the notion of an arbitrary adversary and ask what are the combinatorial properties of arbitrary adversaries that affect connectivity and what you can and can't solve. And that turns out to be actually much simpler than you probably guess. So we'll see you next week.